Hey there! Ever looked at numbers like 3.5, 0.666, or 1.4142 and wondered what's going on with all those digits? Some decimals end nicely, others go on forever, and some just keep repeating the same digits again and again. So here's a mystery worth solving. What do these decimal patterns tell us about the numbers themselves? In this video, we are diving into the world of decimal expansions and how they help us tell the difference between rational and irrational numbers. Let's break it down, digit by digit. Let's break decimals into two big categories. Ready? First up, terminating decimals. These are the polite ones, they stop. Like 1.25 or 0.5. Simple, clean, done. Next, non-terminating decimals. These just keep going. But wait, some of them are repeaters like 0.333 or 7.272727. And some are total wildcards, they go on without ever repeating. So we've got three styles: terminating, non-terminating but repeating, non-terminating and non-repeating. Each one tells us something important about the number. Let's zoom in on rational numbers. Remember, a rational number is any number that can be written as p divided by q, where p and q are integers and q isn't zero. Now here's something cool. Every rational number has a decimal that either terminates or repeats. For example, 1 divided by 4 gives you 0.25, it ends. That's a terminating decimal. 2 divided by 3 gives you 0.666. That's a non-terminating, repeating decimal. So if you ever see a decimal that stops, or one that keeps going in a loop, you're looking at a rational number. Now let's switch gears to irrational numbers, the ones that can't be written as p divided by q. They're decimals? Totally unpredictable. They go on forever, but with no repeating pattern at all. Take square root of 2. It's about 1.414 to 135 and just keeps going with no pattern. Or pi is 3.14159 to 65 and on and on. So here's the key. If a decimal goes on without ending and without repeating, you've got yourself an irrational number. Let's try a few examples, just like the ones in your textbook. Example 1. What about 3.142678? The decimal ends, right? That means we can write it as a fraction. 3.142678 is equal to 3,142,678 divided by 10 lakh. Boom. It's a rational number. Example 2. Let's take 0.3333, repeating forever. Let x is 0.333. Multiply by 10. Now 10x equals to 3.333. Subtract the 2, 10x minus x is 3. That gives x equals to 3 divides by 9 and that is 1 by 3. That's another rational number. So repeating or terminating, still rational. Time for a quick challenge. Can you guess if the number is rational or irrational? Let's go. First, 0.75. It ends. That's a terminating decimal and rational. Next, 2.567567, repeating pattern. That's rational too. Last one, 0.10110111101110. Whoa, no pattern, no end. That one's irrational. Nailed it? Great job, you're becoming a decimal detective. Want a quick trick to tell what kind of number you're looking at? Just follow the decimal. If the decimal ends, it's rational. If it repeats, it's still rational. But if it never ends and never repeats, that's your clue, it's irrational. So next time you see a weird-looking decimal, just ask, does it stop? Does it loop? Or does it run wild? Your answer is hiding in the digits. Okay, but why do decimal expansions even matter? Well, they help us do more than just spot number types. They help us classify numbers as rational or irrational, convert decimals into fractions, and locate numbers accurately on the number line. In short, decimals are like clues. They show us where a number belongs and how it behaves. That's why understanding them is a big deal. Let's wrap it up. In this lesson, we learned that real numbers can be understood by looking at how their decimals behave. If a decimal ends or repeats, it's a rational number. If it never ends and never repeats, it's irrational. These decimal patterns help us identify and classify numbers and even convert them back into fractions. So whether a number stops, loops, or runs wild, its decimal tells the whole story. Up next, we'll explore how to operate with real numbers and simplify expressions like a pro.